Thermodynamics. Thermodynamics is a branch of physics that deals with the relationships between heat and other forms of energy. It is concerned with the study of how energy is transferred between systems and how it is converted from one form to another. Thermodynamics is based on the fundamental laws that govern the behavior of energy and matter, including the first law, conservation of energy, the second law, entropy and energy transfer, and the third law, thermodynamic limits at absolute zero temperature. These laws are applicable to a wide range of systems, from individual atoms and molecules to complex microscopic systems, and have numerous applications in engineering, physics, chemistry, and other fields. Thermodynamics is essential for understanding the behavior of many natural and artificial systems, from the functioning of the human body to the operation of power plants and refrigerators. As we're talking about the definition of thermodynamics, we are now going to discuss the brief overview of the second law of thermodynamics. The second law of thermodynamics is a fundamental principle in physics that establishes the direction of heat flow and the limitation of converting heat into work. It means the second law of thermodynamics, sometimes referred to as entropy, is one of the most significant of these rules. In thermodynamics, entropy is a quantity representing the amount of energy in a system that is no longer available for doing mechanical work, while in philosophy, it is the transition from order to chaos. Heat always flows spontaneously from hot to cold objects. It is impossible to convert all the heat from a hot object into work without also transferring some heat to a cold object. The maximum efficiency of a heat engine is limited by the Carnot efficiency, which depends only on the temperatures of the hot and cold reservoirs. The second law, which outlines the capabilities of the universe, is likely more well-known and deep than the first. This law addresses waste, fading, and decay.
Definition of entropy. Entropy is the amount of thermal energy per unit temperature in a system that is not available for meaningful work. Because work is obtained from ordered molecular motion, entropy is also a measure of a system's molecular disorder or randomness. Entropy is a measurable physical characteristic and a scientific notion that is frequently connected to a condition of disorder, unpredictability, or uncertainty. The notion and the phrase are employed in a variety of disciplines, including classical thermodynamics, where they were initially identified, statistical physics, which describes nature of the molecular level, and information theory. It has wide-ranging use in physics and chemistry, biological systems, and how they relate to life, cosmology, economics, sociology, weather science, and information systems. Particularly the transfer of information through telecommunication.
Entropy change. In 1850, Clausius proposed an idea of entropy as a method of mathematically analyzing whether or not a specific procedure goes against the second law of thermodynamics. The procedure assumes that when an amount of heat, Q, flows into a heat reservoir, at a constant temperature T, the reservoir entropy S increases by S is equal to Q over T. These equations give a thermodynamic definition of temperature that is equivalent to a thermometric definition. The formula for this is delta S is equal to Q over T. Consider two heat reservoirs R1 and R2 at temperature T1 and T2. If a quantity of heat Q flows from R1 to R2, the net entropy change for two reservoirs is delta S is equal to Q over T2 minus Q over T1. This equation shows the entropy change is positive when T2 is greater than T1, indicating an increase in disorder and randomness in the system. Conversely, if T2 is less than to T1, the entropy change is negative, indicating a decrease in disorder and randomness. This equation allows for a precise determination of the directions and magnitude of entropy change in a system, providing a powerful tool for understanding the behavior of thermodynamic processes. The formula for this is delta S is equal to Q or heat flow over T2 or temperature number 2 minus Q or heat flow over temperature number 1. Clausius form states that heat will never flow spontaneously from colder to a hotter region, which can also be expressed as a requirement for the net change in entropy to be positive for a spontaneous flow of heat. This means that the disorder or randomness of the system must increase over time and the value of delta S must be positive. However, when the two regions are at the same temperature, there is no spontaneous flow of heat and the system is in equilibrium. In this case, the value of delta S is equal to 0, indicating that there is no change in the disorder or randomness of the system.
According to the second law of thermodynamics, heat transfer only happens spontaneously between substances with higher and lower temperatures. For instance, heat is the transfer of energy from a temperature that is greater to one that is lower. A cold object in touch with a hot one never becomes colder. Instead, the hot object gains heat from the cold one, increasing its temperature. Friction can also entirely transform mechanical energy, such as kinetic energy, into thermal energy, but it cannot do the opposite. A hot object that is immobile can never naturally cool off and begin to move. Another illustration is the expansion of a puff of gas that is placed into a vacuum chamber's one corner. Although the gas enlarges to fill the chamber, it never gathers in the nook. They might all end up back in the corner if the gas molecules move at random, but it's never seen to happen.
Equation for entropy change of the universe. Delta S universe is equal to delta S system plus delta S surroundings. The change of entropy in reversible process. Delta S is equal to delta S system plus delta S surroundings is equal to 0. The change of entropy in a irreversible process or spontaneous process. Delta S universe is equal to delta S system plus delta S surroundings is greater than to 0.
Comparison of the entropy change for reversible and irreversible process. A reversible process is one that can be reversed to return to the system's initial state, whereas an irreversible process is a thermodynamic process that cannot be stopped in order to return to the system's starting state. While an irreversible process cannot be reversed, a reversible process may. The Clausius inequality. Applying the second rule of thermodynamics at each infinitesimal stage of heat transfer results in the Clausius inequality. According to Clausius, it is impossible to build a device whose primary function is to transfer heat from a cool reservoir to a hot reservoir. The Clausius inequality states that system's entropy must increase in any thermodynamic process. This means in practice that any time you do anything, cook a meal, take a walk, or even sit and relax, you're causing an increase in entropy. And while this may not be particularly meaningful on a small scale, it can add to some significant change over time. So the next time you feel guilty about indulging in license, remember that you're doing something good for the environment. According to the second law of thermodynamics, the entropy of the entire cosmos as an isolated system will always rise over time. The second law also states the entropy change in the universe can never be negative. Entropy is established as a physical characteristic of a thermodynamic system by the second law of thermodynamics and various interactions. The first law of thermodynamics, necessity of energy conservation, can be used to anticipate of operations are prohibited while also supplying necessary parameters for spontaneous process. The second law can be expressed by noting that isolated system subjected to spontaneous evolution cannot experience a decrease in entropy because they always reach a state of thermodynamic equilibrium where the entropy is greatest at the given internal energy. An increase in the combined entropy of the system and environment, often referred to as the arrow of time, explains why natural process cannot be reversed.
Problem solving for entropy using the formula of delta S is equal to U over T. Suppose you have a sample of 1 mole of water at 25 degrees Celsius and you heat it up to 50 degrees, absorbing 50 kilojoules of heat in the process. So, calculate the change in entropy of the system. So, step 1, we must determine the value of initial temperature and the final temperature. So, the value of the final temperature is 50 degrees Celsius and the initial temperature is 25 degrees Celsius. So, after we find the final and initial temperature of the water, we must find the change of temperature. So the formula for that is delta T is equal to final temperature minus initial temperature. So the value of final temperature is 50 degrees Celsius minus 25 degrees Celsius. So 50 degrees Celsius minus 25 degrees Celsius is equal to 25 degrees Celsius. After we find the value of the change in temperature, we must turns it into Kelvin. So the formula for Kelvin is delta T plus K is equal to delta T, and the value of Kelvin is 273.15 K. So the value of our delta T is 25. So we just add the value of the Kelvin and the value of the change in temperature. So 25 degrees Celsius plus 273.15 Kelvin. 25 degrees Celsius plus 273.15 Kelvin is equal to 298.15 Kelvin. After we change the temperature into Kelvin, we must calculate now the change of temperature. As I said, the formula that we are using is delta S is equal to Q over T. So the value of our Q is 50 kilojoules and the value of our temperature is 298.15 So 50 kilojoules divide 298 Kelvin is equal to 0.168 joules or Kelvin. The change in entropy of the water sample is 0.168 joules over K. This means that the disorder of the system has increased as a result of the heating process. The higher the temperature of the water, the greater the degree of disorder, which is reflected in the increase of entropy. Problem solving for entropy using the formula of delta S is equal to Q over T2 minus Q over T1. Suppose you have 1 mole of an ideal gas that expands isothermally and reversibly from 1 liters at 300 Kelvin to 5 liters at 500 Kelvin. So, first step, we must determine the initial and final temperature of the system. The initial temperature of the gas is The initial temperature of the gas is 300 Kelvin and the final temperature is 500 Kelvin. So, step number 2, determine the amount of heat absorbed or released by the system. Since the process is isothermal, the temperature of the gas remains constant throughout the process. Therefore, there is no change in internal energy, and the heat absorbed by the system is equal to the work done on the surroundings. The work done by the gas is given by work is equal to negative P times delta volume, where delta volume is equal to volume final minus initial volume is equal to five liters minus 1 liters is equal to liters. Since the process is reversible, we can use the ideal gas law to express the pressure as P is equal to N times R T times V, where N is the number of moles, R is the gas constant, and V is the volume of the gas. Substitute the values and we have P is equal to 1 mole times 8.314 joules over mole K times 300 Kelvin divide 1 liters is equal to 1 mole times 3.314 joules over mole times Kelvin times 300 Kelvin divide 1 liter. So we have the value of 24.942 joules liters. So now we will substitute the value of work. The previous formula for work is equal to negative P volume is equal to negative 24.942 joules over liters times 4 liters is equal to negative 99.768 joules. So now we will substitute the value of Q is equal to negative work is Q is equal to negative times negative 99.768 joules. Q is equal to 99.768 joules. So this is the value of Q. So now we will solve all of this with the formula of delta S is equal to Q over minus Q over T1. Delta S is equal to 99.768 joules divide 500 Kelvin minus 99.768 divide 300 Kelvin, and we will get the value of 0.333 joules over K. The change in entropy of the gas is 0.333 joules over K. This means that the disorder of the system has increased as a result of the expansion process. The higher the temperature of the gas, the greater the degree of disorder, which is reflected in the increase in entropy.
Relationship between entropy and disorder. Entropy is a measure of disorder. The higher the value, the more disorder there is. Entropy is a thermodynamics term that describes the degree of disorder at the atomic, ionic, or molecular level in a system. Again, the more disorder there is, the higher the entropy. Entropy is a thermodynamic quantity that is proportional to the degree of disorder in all substances and is frequently associated with the amount of disorder in a thermodynamic system. This is due to Rudolf Clausius' claim from 1862 that any thermodynamic process admits to being reduced to the alteration of the arrangement of the working body's constituent parts in one way or another, and that the internal work associated with these alterations is quantified energetically by a measure of entropy change. Entropy in the second law of thermodynamics. According to the second law of thermodynamics, the total entropy of a system never decreases during any spontaneous process. It always either rises or stays constant. The second law of thermodynamics describes how energy degrades as a result of entropy creation during heat transmission between a system and its surroundings at a fixed temperature difference. An important implication of this law is that heat spontaneously transfers energy from objects with higher temperatures to those with lower temperatures, but never in the opposite direction. This is due to the fact that entropy rises when heat is transferred from hot to cold.
Heat transfer entropy. As indicated, entropy is directly linked or proportional to heat. The change in temperature affects the entropy. There are instances that entropy is ignored in the process of heat transfer despite of the relevance of the two subjects, because entropy may or may not help in the study of heat transfer. Heat transfer community depends on its purpose in the study itself. Including entropy may sometimes mess the study or make the subject complicated. So second subject is heat transfer in isolated and non-isolated systems. First, heat transfer is basically the change of temperature of a certain subject due to the difference of temperature inside the system. An isolated system, as indicated, is a separated system where there's no flow of energy in it going in or going out. As stated, basically, a closed system is also called the fixed system, where dW is equals to 0 and dQ is equals to 0. There will be no transfer of energy and it will be a constant system with no disturbance. On the other hand, the open system is in opposite terms for transfer of mass and energy takes place. Okay, so for the next subject, heat engines and entropy. Indicated, as we can see in the paragraph, entropy and heat engines are related, for entropy is created as the heat engine runs. And for the engine to work efficiently, entropy must be minimized. A written equation E is less than or equal to 1 minus Tc Th. It is also stated that QH equals infinity and QC is equals to 0, then the efficiency of the engine is maximized. So basically, in the last part, reservoirs works on the unbalanced entropy by making the cold reservoirs receive the discharge of entropy by the heat reservoirs.
Work can be easily, directly, or converted to heat, but heat is not easily converted to work. To do this, we need special devices such as a heat engine. A heat engine is a device which converts chemical energy of fuel into heat energy, and this heat energy is utilized to convert it into mechanical work. A heat engine receives heat from a high temperature source, then it converts that heat or part of that heat to some work done by our system, usually by a rotating shaft, and then it rejects the remaining heat to a low temperature sink. Now let's proceed. To get the work done by the heat reservoir, we have the formula QH plus QC. QH plus QC. QH is the heat transfer out of the hot reservoir, and QC is the heat transfer into the cold reservoir. So let's work on this problem. A heat engine absorbs 4,500 joules of heat energy from a hot reservoir and discards 2,500 joules into the environment. How much work is performed by this heat engine? So we need to know the variable first. In QH, we have positive 4,500 joules. It's positive because the engine is absorbing heat energy. And for QC, we have negative 2,500 joules. It's negative because the system releases heat into the environment. So as we recall, we have the formula QH plus QC. So let's substitute it. Positive 4,500 joules plus negative 2,500 joules. So we have 4,500 plus negative 2,500. We have the 2,000 joules rather. Sorry. So we have our work for the heat engine, which is 2,000 joules. The Carnot cycle. The Carnot cycle, which consists of two isothermal operations in two adiabatic processes, is the most effective heat engine cycle. In this process, the ideal gas in the system absorbs keen amount of heat from a heat source at a high temperature. Thus expands and does work on surroundings. A Carnot cycle operates as follows. First, it receives thermal energy isothermally from some hot reservoir maintained at a constant high temperatures. Second, it rejects thermal energy isothermally to a constant low temperature reservoir. And third, the change in a temperature is reversible adiabatic process. In a Carnot cycle, a system or engine moves energy in the form of heat between two thermal reservoirs at temperatures referred to as the hot and the cold reservoirs. With some of this move energy being used to drive the system's work, there is no entropy generation and the cycle is reversible. Heat goes from the cold to hot reservoir or heat pump or refrigeration when work is applied to the system. It is only transported between the thermal reservoir and the system without gain or loss of it. The mechanism exerts energy on the environment as heat transfers from the hot to the cold reservoirs. The temperatures of the thermal reservoirs affect how much work is done by the system or engine to the environment in a Carnot cycle, and the amount of entropy that is transferred from the hot reservoir to the system equals the amount of heat that is transmitted from the hot reservoir to the system every cycle. Carnot efficiency describes the maximum thermal efficiency that a heat engine can achieve as permitted by the second law of thermodynamics. The law was derived by Sadi Carnot in 1824. Carnot pondered the idea of maximum efficiency in a heat engine, questioning whether or not the efficiency of a heat engine can approach 100%, or is there an upper limit that cannot be exceeded. Based on direct observations of physical systems, it is clear that thermodynamic processes occur only in certain directions. While the first law places no restrictions on the direction in which a thermodynamic process occurs, it does not ensure that the process is possible. To answer that question, we need another thermodynamic principle or law that tells us something about the natural direction of thermodynamic processes. That principle is the second law of thermodynamics. In order for a process to occur, both the first and the second laws of thermodynamics must be satisfied. There are various ways of stating the second law of thermodynamics. One of the most useful forms of the second law of thermodynamics hereafter referred to as simply the second law. It said that it is impossible for a heat engine to produce an amount of work equal to the amount of heat received from a thermal energy reservoir. In other words, the second law states that it is impossible for a heat engine to convert all the heat it receives from a thermal energy reservoir to work. The feasibility of the new heat engine may be checked by ascertaining whether the heat engine violates either the first or second laws of thermodynamics. If the first law is violated, the heat engine would have to produce an amount of work greater than the amount of heat supplied to it. And if the second law is violated, the heat engine would have to have a thermal energy greater than the Carnot efficiency for a heat engine operating between the same temperature limits. The second law of thermodynamics, while very useful for analyzing and designing engineering systems, is a scientific principle that has no profound consequences. From a scientific standpoint, the second law is considered an arrow of time and an immutable principle that assigns a natural direction to all processes. Stones fall from cliffs but never the reverse. Heat flows from hot objects to cold objects but never the reverse. Raw eggs dropped to the floor make a gooey mess. Cream mixes with coffee but once mix the coffee and the cream do not separate back out. Physical processes are ordered as they follow the arrow of time. Matter spreads, energy spreads, reducing the quality of things. And according to second law, things naturally move from order to disorder, from a higher quality to a lower quality, from a more useful state to a less useful state. In short, the second law says that left to themselves, things get worse.
Physical changes. A physical change is characterized by a change in a physical attributes. Melting, transition to a gas, change in strength, change in durability, changes in crystal form, textural change, shape, size, color, volume, and density are all examples of physical qualities. A physical change affects the form of a chemical but not its chemical content. We can use physical changes to separate mixtures into their constituent compounds, but not to separate compounds into chemical constituents or smaller molecules. When objects or substances undergo to a change that does not change their chemical composition, it is referred to as a physical change. This is contrast to the idea of chemical change, which occurs only when the composition of substances change or when or one or more compounds are combined or broken down to form new substances. To sum up, a physical change can be revised by a physical means, salt dissolved in water, for example, can be obtained by allowing the water to evaporate. Physical change and entropy. Entropy increases as the phase transition from solid to gaseous occurs. The solid has a regular organization and is compact, resulting in a molecular disorder. As a result, the entropy is low. The entropy of a liquid is greater than that of a solid but less than of a gas. Entropy during phase transition as a solid is turned into a gaseous phase. The rate of entropy increases. Entropy is a term that can be discussed thermodynamically as well as how the transmission of energy from form to another affects of entropy. Entropy changes during phase transition. This provides detailed information on how the entropy changes when the phase transition takes place. Since there is a phase change from solid to gas, entropy increases. The solid has regularity, structure, and density, resulting in low molecular disorganization. As a result, entropy is low. The entropy of a liquid is greater than of a solid but less than that of a gas. Entropy only changes during a phase transition as a solid is changed into a gaseous phase. The rate of entropy increases. Entropy is a thermodynamic concept that describes how one change of energy from form to another influences entropy. Solid to liquid, liquid to gas equation. When a solid is heated over its melting point, it becomes liquid because the pressure exceeds that substance's triple point. Intermolecular or intraionic forces remains important, but the molecules have enough energy to move around, making the structure mobile. A liquid can be converted to a gas by heating at constant pressure to the boiling point of the substances, or by reducing pressure at constant temperature. Evaporation is the process through which a liquid transformation into a gas. The solid turns into a liquid when heated past its melting point because the pressure is greater than the substance's triple point. The molecule has enough energy to move around, making the structure mobile, but intermolecular or intraionic forces are still significant. By the boiling at the same pressure or by lowering the pressure while maintaining the same temperature, a liquid can be transformed into a gas. And the process of evaporation is the conversion of a liquid into a gas. Now let's solve this problem. What is the entropy change for 5 mole of H2O undergoing 5 degrees Celsius fusion? In this problem, we are using the formula of delta S is equal to Q over T. Where Q is equal to delta H fusion. T is equal to melting point in K. So let's start. Five mole times 9.008 mole times 10 raised to 3 divide 1 kj over 278k is equal to 162 j over k. Okay, let's proceed for number 2. What is the entropy change for H2O boiling at 300 degrees Celsius evaporation? In this problem, the formula we will use the same formula as number 1. Q is equal to delta H evaporation. T is equal to boiling point in K. So let's start. 1 mole times 2.57 kg over mole times 1000 divide 673k is equal to 30 j over k.
Applications of the second law of thermodynamics. Our number one example for this is refrigerator. A refrigerator is a appliance in a house that moves heat from a space or other enclosed space to a warmer area. This cools down as a result of transferring the heat from this area, keeping food and other items at a cool temperature. According to the second law of thermodynamics, heat spontaneously moves from hotter to colder objects, making it impossible to convert all of the heat into work. In this case, the refrigerator can be used to demonstrate how the second law of thermodynamics can be applied. This law is carried out through the use of a refrigerant, which collects heat from the interior of the refrigerator, colder objects, and releases it to the exterior, hotter objects, through a series of procedures. Despite the fact that heat naturally flows in the exact opposite direction, the situation allows the refrigerator to keep its interior colder than the atmosphere around it. Our next example is power generation. Power generation is a method of creating electricity or additional forms of energy from a variety of sources, including reusable, nuclear, and fossil fuels. The second law of thermodynamics, which says that no energy process of conversion is capable of being 100% efficient and that a certain amount of energy is constantly lost to the surrounding as waste heat, plays an essential role in the production of electricity. This law is applied in power generation system by means of the use of heat engines, which transforms thermal energy into mechanical work through taking benefits of the difference in temperature between a high temperature source and a low temperature source, such as water. Heat proceeds from the source of energy to the engine, where it is converted to work. But because of the law, some of the heat energy is always lost to the environment as waste heat, lowering the entire effectiveness of the process. The impact of second law of thermodynamics in global warming and the greenhouse effect. The second law of thermodynamics is essential for learning about the greenhouse effect and the global warming. Heat constantly flows naturally from hotter to colder objects, according to the law, and it wouldn't be possible to transform all of the heat into work. The gases known as greenhouse gases, such as carbon dioxide and methane, act as a natural insulator in the Earth's atmosphere. storing heat from the sun and keeping it from escaping back into space. This results in a warming effect known as the greenhouse effect. On the other hand, human activity such as the use of fossil fuels have boosted the amount of greenhouse gases in the atmosphere, leading to a more powerful and pronounced greenhouse effect. This results in global warming, which has a wide range of environmental and social consequences, such as rising sea levels, more intense and frequent weather conditions, as well as shifts in ecosystems and biodiversity. Knowing and lowering the impacts of the greenhouse effect and global warming has become essential for ensuring our planet's sustainability in the future.
The importance of the second law in the study of thermodynamics. The first one is the behavior of physical system is fundamentally constrained by the second law of thermodynamics. The second one is the efficiency of energy conversion processes is constrained, and it is informed us that some of energy will always be lost as heat to the environment. The next one is the law places limitation on the direction of heat transfer and other thermodynamic processes, assisting us in determining what is and it's not possible. The fifth one, it plays an essential part in the development and improvement of energy systems and processes in fields like engineering, physics, chemistry, and biology. In the study of subjects like energy conversion, entropy, and the thermodynamic characteristic of materials and systems. The second law of thermodynamics is important. The last one is the understanding the limitation imposed by the second law will help us use energy more sustainably and efficiently, as well as better understand how complex systems behave in the natural world. The second law of thermodynamics is important due to the fact that it implements fundamental constraints on physical system behavior, especially when it comes to energy conversion processes. It indicates to each of us that certain processes, such as heat transfer from a cold object to a hot object, are not possible to accomplish without an extra amount of external work. It further suggests that efficiency of energy conversion processes is limited, and that some energy is constantly lost to the surrounding as heat.
Definition of Gibbs free energy. Gibbs free energy, also known as the Gibbs function or free enthalpy, is a quantity that is used to measure the maximum amount of work done in a thermodynamic system when the temperature and pressure are kept constant. Gibbs free energy is denoted by the symbol capital G. Its value is usually expressed in joules or kilojoules. Gibbs free energy can be defined as the maximum amount of work that can be extracted from a closed system. Hosea Willard Gibbs, an American scientist, discovered this property in 1876 while performing tests to predict how systems would have behaved when joined or whether a process may happen concurrently and spontaneously. It can be imagined as the quantity of usable energy contained in a thermodynamic system that can be used to carry out some work. Gibbs free energy was once known as available energy. Importance of Gibbs free energy. The Gibbs free energy is important because it enables one to predict the direction of spontaneous change for a system under the constraints of a constant temperature and pressure. These constraints generally apply to all living organisms. A reaction that favors the creation of the products is called a spontaneous reaction. Spontaneous reactions are those that have a drop in energy and an increase in entropy. If a reaction is spontaneous, it can be predicted using the G value. Gibbs free energy equation. The formula for Gibbs free energy is G equals U plus PV minus TS, where U is internal energy, the SI unit is joule, and P is pressure, which SI unit is Pascal, and V is volume, and its SI unit is M cube. And we have T as temperature, as SI unit Kelvin, and capital letter S as entropy, and the SI unit of it is joule or Kelvin. And lastly, H is the enthalpy. The SI unit for enthalpy is joule.
Derivation of the Gibbs free energy and equation. The Gibbs free energy, or Gibbs energy as it is more commonly known as symbol G, is a thermodynamic potential that can be used to calculate the maximum amount of work other than pressure volume work. Thermodynamically closed system can be performed at constant temperature and pressure. It also serves as a prerequisite for processes like chemical reaction that may occur under this condition. The change in a system's free energy that occurs during a reaction can be quantified under any set of conditions. When data is obtained under standard state conditions, the outcome is the standard state free energy of reaction delta G. When computing delta G of a reaction, the entropy term is subtracted from the enthalpy term. Because of the way of the system free energy is specified, delta G is negative for any reaction where delta H is negative and delta S is positive. Delta G is thus negative for any reaction that is favored by both the enthalpy and entropy terms. As a result, we can deduce that any reaction of which delta G is negative should be beneficial or spontaneous. So let's solve this problem. Predict whether the following reaction is still spontaneous at 300 degrees Celsius. Nitrogen gas plus hydrogen gas is equal to ammonia gas. Assume that delta H is equal to 9.220 kgmol and delta S is negative 198.75 kgmol. So in this problem, the formula we are using is delta G is equal to delta H minus T delta S. So let's start. 92.220 J minus 507 times 1/8 JK. Bring down 92.220 J minus 573K times negative 1.98.75 J is equal to negative 13,800 J is equal to 92.220 J times 13,800 joules equal to 21,500 180 joule. So the final answer is delta G is equal to 21.6 kJ. So next, number 2. Predict whether the following reaction is spontaneous or not at 35 degrees Celsius. Nitrogen gas plus nitrogen gas is equal to ammonia gas. The formula we use is same as number 1. Delta G is equal to delta H minus T delta S. T is equal to 35 degrees Celsius plus 273.15 is equal to 308.15 K. So let's start. 92.220 J minus 308.15 K times negative 198.75 J K. Bring down 92.220 J plus 61.250 J is equal to 30,970 J. The final answer is delta G is equal to 30.97 AJ.
Significance of Gibbs free energy value. If delta G is negative, the reaction is spontaneous. If delta G is positive, the reaction is non-spontaneous. If delta G is at 0, the system is at equilibrium. Gibbs free energy can be used to predict reaction spontaneity. For us to predict the reaction, we need to know that a negative value for G means that the process will move in advance to reach equilibrium. And so if the Gibbs free energy for the specified process is negative, the reaction will occur spontaneously. A positive value for G means that the process will move in reverse to reach equilibrium. And the positive value means the reaction is non-spontaneous. And the value for G of 0 means that the system has reached equilibrium. Reaching the equilibrium means that the concentrations of the reactant and product are no longer changing and are constant. Explanation of how Gibbs free energy can be used to predict reaction spontaneity. Gibbs free energy looks into enthalpy and entropy, the two primary factors that help in the initiation of chemical reactions. Entropy is a measure of the degree of disorder in a system, while enthalpy refers to the amount of heat it contains. Because both entropy and enthalpy have positive and negative values, it can be used to determine the spontaneity of chemical reaction when analyzed independently. It is possible to predict mathematically whether a reaction will occur spontaneously or not using the Gibbs free energy equation. Using delta G, the equation is expressed as where delta G is the change in Gibbs free energy, delta H is the change in enthalpy, T is the temperature in Kelvin, and delta S is the change in entropy. As this chart shows, enthalpy represents one way to assess the spontaneity of a reaction. When delta H is less than 0 or a negative number is present, for instance, the reaction is exothermic, which means that heat is released from the system. Exothermic reactions are spontaneous. The reaction is endothermic in contrast when delta H is greater than 0 or a positive value, and the system absorbs heat from its surroundings. Endothermic reactions are non-spontaneous. So let's do some example. So let's solve. Calculate the reaction at 25 degrees Celsius. We have the given delta H is equal to negative 176 kilojoule and delta S that is equal to negative 284.8 joules per Kelvin. So to solve, we calculate delta G from this formula. Delta G equals to delta H minus temperature delta S. But first, we need to convert the units for delta S into kilojoules per Kelvin and temperature into Kelvin. To convert, all we need to do is to divide by 1000. So delta S that is equals to negative 284.8 joules per Kelvin multiplied by 1 kilojoule divided by 1000 joules. And so we have negative 0.284.8 kilojoules per Kelvin. And now our temperature needs to be in Kelvin. So 273 Kelvin plus 25 degrees Celsius is equals to 298 Kelvin. Now that we have converted the units, the definition of Gibbs energy can then be used directly. We will just follow our formula. Our delta H is negative 176 kilojoule minus our temperature, which is 298 Kelvin, multiplied by our delta S, which is negative 0.284.8 kilojoules per Kelvin. So we multiply 298 Kelvin to 0.284.8 and we are left with negative 84.9 kilojoule. And then we minus 176.0 kilojoule to negative 84.9 kilojoule, and so our delta G is equals to negative 91.1 kilojoule. Keyword negative. Since our delta is negative, this reaction is spontaneous.
Use of Gibbs free energy in chemical equilibrium calculations. Chemical equilibrium is a stage in chemical process in which the concentration of both products and reactants approach a limit that prohibits further deviation. We can use the formula shown. The change in Gibbs free energy equals to 0 and Q is equals to K. Therefore, the equation we will use is the standard change in Gibbs free is equals to negative RT multiplied by the natural log of K. The K in all of this equation is equilibrium constant. I will give an example to solve as we further understand the equation. The equilibrium constant for the following reaction is 1.6 times 10 raised to the power of negative 10 at 30 degrees Celsius. Calculate the delta G standard. Standard change in Gibbs free energy is equals to negative RT multiplied by the natural log of K is the formula that we will use. For example, standard change in Gibbs free energy is equals to negative 8.314 joules per Kelvin dot mol times 303.15 K multiplied by the natural log of 1.6 times 10 raised to the power of negative 10. The total of this problem is negative 56,850 joules per mol. If we cancel the units correctly, the answer will be in joule per mol rather than K joules per mol, rounding the right number of significant number and converting to the standard units for free energy values. Gibbs free standard is equals to 57 K joule per mol for this reaction. This is fairly significant value, showing that the reactants are greatly preferred as would be expected for a moderately insoluble ionic compound.
Explanation of how change in temperature and pressure affects what gives free energy. The effective Gibbs free energy is dependent upon on the entropy, the measure of a system's thermal energy per unit temperature that change in temperature and pressure. On the increasing temperature, the Gibbs free, the energy will increase or decrease, and it will depend on the entropy of the given reaction. There are many factors affecting Gibbs free energy, such as when the partial pressure of the reactant gas increases, the Gibbs free energy becomes more negative, but when the partial pressure of the product gas increases, the Gibbs free energy also becomes more positive. When the entropy of the system increases, that is the reaction release, the Gibbs free energy becomes more negative and vice versa.
Okay, so my topic will be the Gibbs free energy and kinetic reactions. The Gibbs free energy of a system at any moment in time is defined as the enthalpy of the system minus the product of the temperature times the entropy of the system. So G is equals to H minus Ts. That is the formula for the Gibbs free energy of the system or enthalpy of the system. The Gibbs free energy of the system is a state function that because it is defined in terms of thermodynamic properties that are state functions. The change in the Gibbs free energy of the system that occurs during a reaction is therefore equal to the change in the enthalpy of the system minus the change of the product of the temperature times the entropy of the system, also written as delta G is equals to delta H minus delta time of the entropy of the system multiplied by temperature. If the reaction is run at a constant temperature, this equation can be written as follows. Delta G is equals to delta H times delta S. The change in the free energy of a system that occurs during a reaction can be measured under any set of conditions. If the data are collected under standard state conditions, the results is the standard state free energy of reaction, also called as delta GO. So delta GO is equals to delta HO minus T delta SO. The beauty of the equation defining the free energy of a system is its ability to determine the relative importance of the enthalpy and entropy terms as driving forces behind a particular reaction. The change in the free energy of the system that occurs during a reaction measures the balance between the true driving forces that determine whether a reaction is spontaneous or, as we have seen, the enthalpy and entropy terms have different sign conventions. Because of the way the free energy of the system is defined, delta GO is negative for any reaction for which delta HO is negative and delta SO is positive. Delta GO is therefore negative for any reaction that is favored by both the enthalpy and entropy terms. We can therefore conclude that any reaction for which delta GO is negative should be favorable or spontaneous. Conversely, the delta GO is positive for any reaction for which delta HO is positive and delta SO is negative. Any reaction for which delta GO is positive is therefore unfavorable. When a reaction is favored by both enthalpy and entropy, there is no need to calculate the value of delta GO to decide whether the reaction should proceed. The same can be said for reactions favored by neither enthalpy nor entropy. Free energy calculations can become important for reactions favored by only one of these factors. Thank you.
As we are discussing the Gibbs free energy, I will provide a brief recap in this section. Because it is defined in terms of thermodynamic parameters that are state functions, the Gibbs free energy the system is a state function. The change in the system's Gibbs free energy that happens during a reaction is thus equal to the change in the system enthalpy minus the change in the product of the temperature times the system's entropy. Delta G is equals to delta H minus delta times Ts. The change in a system free energy that happens during a reaction may be quantified under any set of conditions. If the data are gathered under standard state condition, the outcome is the standard free energy of reaction. The equation of the Gibbs free energy is standard change in Gibbs free energy is equals to delta standard H minus T delta standard S.
In conclusion, Gibbs free energy is a crucial concept in thermodynamics and chemistry as it helps to determine the spontaneity and feasibility of chemical reactions. It considers the enthalpy and entropy of a system, which allows for a more comprehensive understanding of the thermodynamics of a reaction. The Gibbs free energy equation is also useful in predicting the conditions under which a reaction will occur, and determining the equilibrium constant of a reaction. Furthermore, Gibbs free energy can be used to understand the behavior of biological systems such as the energy transformations that occur during cellular respiration. Overall, an understanding of Gibbs free energy is essential for anyone studying or working in the fields of thermodynamics and chemistry.